Hey everyone, and welcome to today's Explainer. I am so incredibly excited to be here with you because today we have a really fascinating goal. We're going to systematically break down the architecture of Kubernetes. Now you might be wondering, why does this matter? Well, it's simple. Kubernetes has absolutely revolutionized how the modern web operates. We're going to take this massive, sometimes pretty intimidating topic and distill it into clear, easy-to-grasp pieces. By the end of our time together today, you are going to walk away with a really solid, confident understanding of how this whole system actually works under the hood, and honestly, why it's so brilliant. But first, I want you to just think about the fundamental problem developers face every single day. Look, containers are a fantastic way to bundle and run your applications, for sure. But the second you move to a real, true production environment, the complexity just explodes. Picture this. It's Black Friday, it's 2 a.m., and your e-commerce site suddenly gets a massive, totally unexpected spike in traffic. A server overloads and boom, a container goes down. You absolutely cannot afford to have some sleepy engineer wake up, log in, and manually start spinning up replacement containers in the middle of the night just to stop an outage. So, how do you manage thousands of these containers, scale them up and down instantly, and ensure absolutely zero downtime without manually watching over them 24/7? Wouldn't it be amazing if this was handled entirely by a vigilant, automated system?
Well, that is exactly where Kubernetes steps in to save the day. By its official definition, Kubernetes is a portable, extensible, open-source platform specifically designed for managing containerized workloads and services. But let's translate that into plain English, right? It facilitates what we call declarative configuration. And declarative configuration just means you tell Kubernetes exactly what you want the final result to look like. You basically say, hey, I always want 5 copies of my app running, and Kubernetes completely figures out how to make that happen on its own. It's the ultimate system that steps in to orchestrate the chaos of distributed systems seamlessly, giving you automated rollouts, self-healing, and horizontal scaling.
Okay, let's dive into this. Here is our roadmap for today. 1. Meet the Kubernetes cluster. 2. The control plane. 3. The worker nodes. And 4. Deploying an application.
All right, part 1. Meet the Kubernetes cluster.
When you look at the blueprint of this entire setup, you'll notice a very clear separation into 2 main domains. On one side, you have the control plane node containing components like the API server, etcd, and various managers. On the other side, you have the worker nodes, which hold things like kubelets, kube-proxies, and your actual application pods. Now, if you're looking at all those terms and feeling just a little overwhelmed by the jargon, please do not panic. We're going to break down every single one of these scary-sounding terms individually. For now, just recognize that every cluster needs at least one worker node to run pods, but in a real production environment, you're going to have multiple nodes, and the control plane will run across multiple computers to keep everything highly available. To make this incredibly easy to remember, I really want you to think of this entirely in terms of brain versus brawn. The control plane, that's the brain. It makes the big global decisions about the cluster, like scheduling, and it detects and responds to cluster events. The worker nodes, that's the brawn. They are the physical or virtual machines that actually host the application pods and do the heavy lifting of running your workloads. And just like in biology, these two desperately need each other. A brain without brawn is just a bunch of brilliant ideas with literally no way to interact with the world. But brawn without a brain, that's just chaotic, unguided power that usually breaks things. They have to work together in perfect harmony. Moving right along to part 2, the control plane. So, let's zoom in and really understand that brain. The very first component of the control plane we've got to talk about is the kube API server. Now, control plane components can theoretically run on any machine in your cluster, but to keep things nice and organized, setup scripts usually start them all together on the same dedicated machine. As for the name, kube API server, well, developers aren't exactly known for poetic names, but it tells you exactly what it does. Think of the kube API server as the front desk receptionist, or actually, maybe a better word is the bouncer of the cluster. It's the core component that exposes the Kubernetes HTTP API, acting as the absolute front end for the entire control plane. Nobody gets to talk to the brain without going through this API server first. It's the sole interface where administrators, users, and even other internal components direct Kubernetes. And here's the best part. It's designed to scale horizontally. If your cluster gets insanely busy and the bouncer gets overwhelmed, Kubernetes simply scales by deploying more instances of the API server and balancing the traffic effortlessly between them. But a brain needs a memory bank to remember everything it was told to do, right? The API server takes for requests, sure, but where does it actually store all that vital information? That brings us to etcd.
etcd is officially described as a consistent and highly available key value store. Let's simplify that. A key value store is basically just a digital dictionary. You look up a specific name and it hands you the specific value attached to it. For Kubernetes, this is the ultimate, highly secured ledger of the cluster. Every single piece of state data regarding your cluster lives right here. Because it holds the master record of what your cluster should look like, the official documentation issues a very stark warning. You absolutely must have a reliable backup plan for this data. Seriously, if your server crashes and you lose your etc data, the brain literally gets amnesia. It will have zero idea what applications are supposed to be running. Okay, so the memory is securely stored in our ledger, but who actually delegates the tasks based on those memories? Enter the cluster's ultimate matchmaker, the kube-scheduler. The kube-scheduler is a seriously intelligent component. It constantly watches that API server for newly created pods that don't have an assigned worker node yet. When it spots a homeless pod, its job is to select the absolute optimal node for that workload to run on. And it doesn't just guess, okay? Let's say you have an application that requires a massive, high-powered GPU to run a machine learning algorithm. The scheduler looks at all the available nodes, instantly filters out the weak ones that lack a GPU, evaluates the remaining hardware constraints, and assigns the pod exactly where it has the perfect resources to succeed. Next step, we group the final pieces of the control plane together, the controller managers. To understand these, think about what a controller actually is in the real world. Think about the thermostat in your house. It constantly checks the current temperature, compares it to the temperature you actually want, and then kicks on the AC or heater to fix the difference. Kubernetes controllers do the exact same thing for your cluster's desired state. There are two distinct types of managers checking this temperature. First is the internal kube controller manager. You can kind of think of this as your internal HR department. It handles a lot of internal processes, like the node controller that notices when an internal computer goes offline, or the job controller watching for one-off tasks. To keep things lightning fast, these are all compiled into a single binary. Second is the optional cloud controller manager. This is basically your external PR rep. It embeds cloud-specific logic and lets your cluster talk directly to the outside world, like an AWS or Google Cloud API, to set up things like external load balancers.
All right, let's shift gears to part 3, the worker nodes.
Now that we've mapped out the brain, let's explore the brawn of our operation. The worker nodes can be physical servers sitting in a rack somewhere or virtual machines up in the cloud. Think of a worker node like a massive cargo ship. Its primary job is to host your application workloads within what Kubernetes calls pods. If the node is the cargo ship, the pods are the standard shipping containers neatly stacked on the deck. They're the smallest deployable units of computing. These nodes provide the essential runtime environment. And while they do the physical heavy lifting, remember our rule. They are managed entirely by the instructions coming down from the brain. But to take orders from the control plane, every cargo ship needs a dedicated agent on the ground to oversee the deck. And that primary agent is the kubelet. So the really crucial point here is that the kubelet is the ultimate foreman of the node. It takes a set of instructions from the brain, called pod specs, and actively verifies that the containers described in those specs are built, running, and most importantly, healthy. It actually accomplishes this by constantly checking the pulse of the application, using what Kubernetes calls a liveness probe. If that pulse stops and the app freezes up, the kubelet doesn't sit around asking for permission. It ruthlessly kills the frozen container and restarts a fresh one to ensure your customers never even see an error screen. Aside from our foreman, the kubelet, there are two final essential pieces found on every single worker node. Because getting a shipping container onto the deck is only half the battle, right? That container needs to be able to communicate with the world, and it needs a physical engine to actually power on. That brings us to the kube-proxy and the container runtime. Think of the kube-proxy as your local traffic cop. It's a network proxy living on each node that maintains the network rules, making absolutely sure that when a web request comes in, the traffic cop directs it flawlessly to the correct pod. Finally, the container runtime is the fundamental engine itself. This is the actual software, like Containerd or CRI-O, that is responsible for unpacking and running the container. The foreman, the kubelet, tells it what to do, but the runtime actually turns the key and starts the software. Which brings us to part 4. Deploying an application. And this brilliantly illustrates the entire architectural workflow in action. We're going to walk through this just like a high-speed relay race. Step 1, the starting gun fires when a user hands a desired state configuration to our bouncer, the Kube API server. Step 2, the API server authenticates it and passes the baton to etcd, writing the request down in stone in the master ledger. Step 3, the kube-scheduler grabs the baton, realizes a new pod needs a home, evaluates the brawn available, and assigns it to the absolute optimal worker node. Step 4. The foreman, the kubelet, on that specific node catches the baton as it crosses the finish line. It talks to its container runtime, the engine fires up, and the application pod is physically created. The desired state has dynamically become the actual state. It truly is just a beautifully orchestrated system of distinct, single-purpose components working in absolute harmony. By eliminating the constant fear of midnight crashes and manual server scaling, Kubernetes completely frees developers to focus entirely on writing incredible software. Now that you understand the powerful brain and brawn of the Kubernetes architecture, the question really isn't how to run your workloads anymore, but rather, what massive scale of applications are you going to build next? Thank you so much for joining me in this